Well, what I'd like to do today is talk about Seasons 1. I'm going to break this smooth draw project into two to finish talking about that picture you see down towards the bottom. Seasons is something that actually affects the Earth every year, where we get four different, at least here in Northern Virginia, we get four different seasonal patterns. Very definite winter, very definite spring, definite summer, definite fall. There are locations on the planet, usually closer to the equator, but I've heard Seattle, Washington, usually between the 40s and the 70s all year long. If you go down to San Diego, usually 70s, 80s in the day, down to 60s, maybe 50s at night. But if you go down towards the equator, it's usually just like a tropical condition all year long. First thing I want to do is talk about why we don't have seasons. Take a look at this first picture. This actually talks about a couple of things. Look at this word right here. This is called aphelion. This is called perihelion. Helion comes from the name Helios, which is the god of the sun. Aphelion means where it's farthest from the earth, and we actually have two distances. I have my kids know at least one of these. 150 million, that's 10 to the 6th kilometers. Or, the one I want them to know, because it's in the unit that we understand, or the unit we use, 93 million, or 10 to the 6th miles. Okay, so this is what is normally called one astronomical unit. This is a different way of actually categorizing distances in space. When miles and kilometers, the numbers get too large for us to actually be able to see, to imagine, we flip it over. So now all of a sudden Pluto, instead of being billions of miles away, is just 39 AU. Or Jupiter, 5.2 AUs, something that's actually relatively easy to understand. And Earth, of course, 1 AU. It's a very easy number to understand. Put this in a different way, here's the sun. Sun aphelion, where it's farthest away, greater than, this is going to be greater than these numbers. This one's going to be less than these numbers. So if we get a number greater than 150, the sun actually appears smaller. If we get a number smaller than 93 million or 150 million, we get a sun that's actually larger, and you can see the difference is a little bit. The coolest thing to actually understand is that this actually happens in July. So we have our farthest sun in July. Doesn't make any sense for northern hemisphere, at least. And we have our biggest sun in January. And you can see the numbers there, especially if I get rid of those. The numbers are a little bigger than 150 and a little smaller than 150. Altitudes, you can see one altitude is a lot smaller than the other. That only coincides with the fact when the sun actually got to be as big as it's going to be, or as small as it's going to be. It has nothing to do with the season itself. Okay, so we have the same thing when we actually have, and actually let me do this thing. Earth actually goes around the sun in a beautiful counterclockwise direction. So we revolve around the sun this way. We orbit in a counterclockwise direction. The moon orbits in a counterclockwise direction. And the Earth rotates in a counterclockwise direction. This moon also, it's got a synchronous orbit, but it also moves in a counterclockwise direction. That actually plays true for all the planets, asteroids, other things. So it actually is one way we can, one measure of proof that the solar system was created at the same time, the same way. We're not haphazardly going around in different directions. Okay, the moon actually has the same sort of thing. You can see right there perigee and apogee. Apogee meaning far Earth. Moon is farthest from the Earth. It's a name that's also associated with satellites. When they want to come in, they dip in closer to the Earth or farther. And then we have perigee, which is the close. This deals with something that's 250,000 miles. So this one would actually be greater than that, and this one would be less than that, making the moon look smaller or larger. And this will actually make a very important means when we start talking about solar eclipses. What happens when we get a small moon trying to cover a large sun? And in the sky, they have the same apparent size. If you actually hold your index finger up at arm's length, you can cover the sun or the moon by very easily by about 100%, 200%. You could actually cover, if the moon and the sun were sitting right next to each other, you could cover both of those with your index finger at arm's length. Okay, so why do we have seasons? We have seasons because of the tilt of the Earth. If you look at this line, which is called the ecliptic, this is the orbit of the Earth going around, and again it is in a counterclockwise direction. Again, it's 150 million kilometers, 93 million miles average, 1 AU. If you look at that ecliptic line, the Earth is not straight up and down, it's actually tilted at 23.5 degrees. This would be straight up and down. But we're tilted. We're also tilted in the same direction all year long. We're pointed toward a star way up high, which is called Polaris. So this tilt is what gives us seasons. Sometimes we tilt in towards the sun, and what that does is that makes the northern hemisphere, and if you take a look at this line right here where this individual would orbit around, spend a lot more time on the sunny side warming up and a little less time on the dark side cooling down. And if you do the same thing, they're going to orbit this direction. If you do the same thing on this side, they spend more time cooling down and they spend less time warming up. So you can see why we would actually have a summer for the northern hemisphere, it's the winter for the southern hemisphere, and the winter for the northern, summer for the southern. If you take a look at the North Pole, as the North Pole actually rotates in a counterclockwise direction, it does so completely lit up. The South Pole down here, same thing, all rotating the same direction, does so completely in the dark. And then 6 months later, this would actually be June, this would be December. North Pole completely in the dark, South Pole completely lit up. Okay, so let's talk about this diagram, the last one I'm going to talk about today. This diagram actually has all 4 seasons. I'm just going to number it 1, 2, 3, and 4. This has all 4 seasons, and these 4 seasons actually are called the summer, the autumnal, or autumn, winter, and this is the vernal, or spring. They happen in June, they happen in September, they happen in December, March, 3 months away from each other. Let's talk about this one right here. Notice that this axis is tilted. It's tilted 23.5 degrees. Notice that it says we're actually moving in a counterclockwise direction, so the Earth actually goes this way. Does that for all of these. I'm drawing this line over the equator, which is the line of infinite dots halfway between the North Pole and the South Pole. This is called the summer solstice. It's called summer because it's the warmest temperature, and the northern hemisphere actually decided what season was which. It's called the solstice because the sun stands still. If we actually went to this location right here, and the Earth would be at that location, probably should draw a different color. The Earth would be at this location, probably May sometime, because this is March, and April would be in there somewhere, and May, probably late May. What we would do is we actually looked at the sun, and remember when we talked about the celestial sphere, the sky dome? If we draw a north and a south, the meridian is the line that actually goes from the south compass point up to your zenith, and then back down to the north. So when the sun crosses the meridian, it's actually supposed to be the highest elevation. If you would have looked at it here, it would have been lower than if you looked at it here. And every day we move, the sun gets a little higher in the sky, and it keeps doing that until it stands still, because the very next day it's going to start going back down. So this is called a solstice, sun standing still. This is the summer solstice. 3 months later, the sun will have dropped down, so it's about halfway to the lowest point, which is going to receive over here in position number 3. This point, what happens is that the dark area moves closer and closer and closer to the North Pole as we move here. This is the dark side of the Earth. The dark side of the Earth on this one is the side we can't see because the sun sitting in here in the center. Not a good color for the sun. The sun sitting over here in the center is actually illuminating the side that's facing it, so the dark side's facing away. The North Pole is going to kiss the sun goodbye. The South Pole, which has not seen the sun since here, is going to see the sun for the first time in 6 months. This is called the equinox, where if we're located about right here, so this is our counterclockwise orbit around the planet, we experience about 15 hours of daytime heating and only 9 hours of nighttime cooling. In number 2, the entire planet gets 12 hours of heating up, 12 hours of cooling down. So, from the North Pole to the South Pole, 12-hour day. That's called an equa, because it's equal, nox, because it's night. It's called an equinox. 3 months later, that's September 22nd. This is my anniversary. This is my wife's birthday. This is real close to the winter break, Christmas. Don't know what really March stands with, otherwise it's pretty close to a really early Easter. 3 months later, the North Pole has kissed the sun goodbye for 6 months. You can see now it's doing its orbit completely in the dark. The equator actually is now a little bit higher. This actually smacked right smack on the equator. This one's hitting up here, down here a little lower. This one was hitting up here a little higher, and this one's going to be hitting back again, the dark side facing toward us, the light side facing the sun, right smack on the equator. But this winter solstice, where the sun gets lower and lower and lower and lower and lower and lower and lower to the lowest point, the sun stands still again, but now it's really low, for at least for the northern hemisphere. This is going to happen around December 21st, where the northern hemisphere, if you take a look at it, here we are again. We get about 9 hours to heat up, but we get 15 hours to cool down. Pretty obvious why our summers are warmer than our winters. Doesn't work so well for the southern hemisphere. 3 months later in March, we get another equinox where the entire planet gets 12 hours of, I'll do it this way, 12 hours of day, 12 hours of night. We get another equinox, and this is called the vernal equinox. These two are exactly the same. The only real difference is one is getting warmer for the northern hemisphere, the sun's getting higher in the sky. The other one's getting colder for the northern hemisphere, the sun's getting lower in the sky, opposite for the southern hemisphere. But this is the reason we have seasons. It's all about the tilt. Thank you much.